Well, hello again. So today we're going to continue our discussion on amino acids. We're specifically going to be focusing on the D/L classification and R/S absolute configuration of amino acids with some notable exceptions. Don't gatekeep these videos. If you have a friend who's currently studying for the MCAT, be sure to share the playlist with them. It really helps the channel grow and I would really appreciate it. So we're going to start this discussion by talking about chirality. So although this isn't an OChem lecture, we're going to talk briefly on chirality and then we'll move on to apply it to amino acids. So what is a chiral center? It is a carbon atom that's attached to 4 unique groups. So if we look at this carbon atom right here, so this overall structure is methanol. This carbon is attached to 4 groups, however 3 of them are identical, and so therefore it is achiral. This next structure over here is attached to 3 unique groups, but again we need 4 unique groups, so it is achiral. Finally, this structure right here, which is a structure of lactic acid, if you look at this carbon specifically, because we've already established that the carbon atom over here is not going to be chiral, so this carbon atom over here is attached to 4 unique groups. One over here, the carboxylic acid, the hydroxyl group, the methyl group, and finally the hydrogen atom that's implicit over there. So it is indeed chiral. All right, so now let's move on to assigning R/S absolute configurations. So in order to assign configuration to a molecule, you need to first assign priority to the groups that are attached to your chiral center. The way you assign priority is you determine which atom has the highest atomic number, and that will be the highest priority, and then the subsequent one will be the one, the next highest atomic number, and so on and so forth. So if you look at the structure of lactic acid once again over here, this carbon atom is attached to an oxygen atom, hydrogen, a carbon here, and a carbon. So the highest priority is going to be oxygen. Next, you can see right here that you have 2 carbon atoms. So how do you decide which one is going to be the second highest priority? Well, when you have an identical atom, you want to look at the next atom that's attached to your carbon atom in this case. So here you have an oxygen attached to that carbon atom. Over here you have a hydrogen atom attached to the carbon atom. And so therefore, this will have a higher priority, the carboxylic acid group. Okay, and then finally it'll be the methyl group. So now once you've assigned priority, you want to rotate about these groups. So you start from 1 to 2 to 3. So it'll look like this. So you're going counterclockwise, or if you don't want to think of it in terms of like clockwise or counterclockwise, you can imagine yourself at the 12 o'clock position and then say, are you turning left or right? If you're turning left, or again, if you're going counterclockwise, it's going to be S. All right, and then this over here is the enantiomer of S-lactic acid. So that it's the exact same molecule, but it's arranged differently. Enantiomers are non-superimposable mirror images, but we're not going to get into that because this isn't an OChem lecture after all. So you can try the assigning the configuration over here, but I'll just speed through this. So this is the R enantiomer of lactic acid. All right, so this over here is the amino acid backbone, as you are probably familiar with. Right now, this central carbon atom is the alpha carbon, and then you have a carboxylic acid group, an amino group, an R group, and a hydrogen atom attached to that central carbon. And because they're all unique groups for all amino acids, with one exception as we'll discuss later, amino acids will be chiral. Okay, so before we actually assign configuration to amino acids, we're going to quickly shift gears and talk about D/L classification. So the very important point here is that the vast majority of biologically active amino acids are classified as L amino acids. So for the purposes of the MCAT, really, whenever they ask you about a biologically active amino acid, that is an amino acid that's incorporated into like human or plant or whatever it may be, like human proteins, then you know that that is an L amino acid. All right, so how do you determine, like let's say they give you a structure and they tell you, is this L or D amino acid? Well, it's based on the glyceraldehyde molecule. So if you look at the glyceraldehyde molecule, if this OH is to the left, then you have the L glyceraldehyde molecule, and if the OH is to the right, then you have the D glyceraldehyde. So essentially the same thing with amino acids, importantly with the Fisher projection. So this only works with the Fisher projection. You want to have the carboxylic acid group pointing toward, upwards and the R group pointing downwards. And then if your amino group is to the left, then you have the L amino acid, and if it's to the right, you have the D amino acid. All right, so what is the relationship between D/L classification and R/S absolute configuration? All L amino acids will have the S absolute configuration, with two exceptions, as we'll see in a bit, and those are glycine and cysteine. So if you look at this over here, this is alanine, but really you can replace it with any other amino acid besides those two. And if it has the L classification, it'll have the S absolute configuration, and if it has the D classification, it'll have the R absolute configuration. Now, you might object here that, well, look at this amino group. It's pointing towards the right, and we said that if the amino group is pointing towards the right, this should be D-alanine. But the idea here is that only works if you have a Fisher projection, as I mentioned earlier. So don't attempt to assign the classification based on a structure that's not in the Fisher projection. Okay, so now let's assign absolute configuration to this amino acid right here. So standard amino acid, let's say any amino acid but glycine or cysteine, because those are exceptions. So the highest priority group is going to be the amino group, because N has a higher atomic number than carbon right here. So it'll be number 1. Number 2 will be the carboxylic acid, and then number 3 will be the R group. Okay, so this amino acid appears to be in the R absolute configuration, right? Because you're going from 1, 2, 3. So if you're going clockwise, or if you imagine yourself at that 12 o'clock position, you're turning right, then that's going to be the R absolute configuration. But actually, it's not R. It's in the S absolute configuration. And this was a bit of a trick example, but I think I purposely wanted to do this because now I think you'll never forget this. So when the hydrogen atom is coming out at you at a wedge, you need to reverse the configuration. So you assign priority as you normally would. Once you determine the absolute configuration, you just reverse it. All right, so moving on to the exceptions that we mentioned earlier, glycine is neither D/L nor R/S. And that's because it is achiral. So if you look at the structure of glycine over here, it has that carboxylic acid and the amino group attached to the alpha carbon. However, if you look at the other atoms attached here, they're both hydrogen atoms, and if you have two of the same group, then it is achiral. Okay, so that's easy. Now, cysteine is a bit more tricky, okay? So recall how we said that if an amino acid is in the L classification, then it'll have S absolute configuration. But this is not the case for cysteine. So this is actually false. And let's walk through assigning priority, and we'll see why. So here the highest priority group is going to be the amino group, just like any other amino acid. The second highest, recall in every other amino acid, is going to be that carboxylic acid group. However, over here, the second highest, if we're comparing these two atoms right here that are attached to the central or the alpha carbon right here, you have this one is a carbon attached to a sulfur atom, and this one is a carbon double bonded to oxygen. Well, because sulfur has a higher atomic number than oxygen, then therefore, this group right here, the R group, the side chain, will have a higher priority. So therefore, it'll be number 2. And then finally, the carboxylic acid will be number 3. And so that's why the L form of cysteine will actually be rotating towards the right, or if you're at the 12 o'clock position, you're going towards the right, or clockwise rotation, then it's R-cysteine. So you need to remember this. If they tell you, for example, is this amino acid, let's say, for example, S-cysteine, biologically active? Will it be incorporated into human proteins, for example? Can ribosomes incorporate it into proteins? You might initially think yes, because recall how all the other amino acids, if they're in the S absolute configuration, then they have the L classification, and the L classification is the one that will be incorporated into proteins. However, in the case of cysteine, you need that R absolute configuration, which has the L classification and will be incorporated into proteins. All right, so now we're going to go over these quick knowledge checks. So you can pause the video here and attempt to do these on your own, but let's dive right in. So for the following amino acids, provide both the D/L classification and the R/S absolute configuration and determine whether or not they are biologically active. Also down here it says bonus points if you can identify these amino acids. Now I don't expect you to know these at this point because we haven't went over the individual amino acids yet. That's for another video. But let's get started right here. So if we're starting off with this one, you have the amino group, the highest priority, and then recall that for every amino acid except cysteine, carboxylic acid group will have the second highest priority. Now don't get tripped up between methionine and cysteine because these are the only two amino acids that contain sulfur in their side chain. But the difference is that in cysteine, as we saw earlier, the sulfur atom is attached directly to the first carbon after that alpha carbon. So it'll be like, this is that first carbon, it would be attached right here. Whereas in methionine, there are two carbon atoms between the central alpha carbon and your sulfur atom. So it's not an exception like cysteine is. Okay, so now this is number 3. So you're rotating in this direction. In other words, you're going counterclockwise. So this is the S amino acid. And then recall how we said all S amino acids, with the exception of cysteine, are also L amino acids. So it is indeed biologically active. Now let's take a look at this amino acid right here. So I would encourage you when you are dealing with Fisher projections, don't attempt to assign absolute configuration, and don't even attempt to redraw it. So this right here, this amino group is on the left. So therefore, this is an L amino acid. So even if they ask you for the absolute configuration, once you decide what the classification is, you can say, okay, if it's any amino acid other than cysteine, then the L amino acid will be in S absolute configuration. All right, finally, we have the structure of valine over here. So again, valine is not an exception. So you would go, the amino group is 1, the carboxylic acid group is 2, and then finally the side chain is 3. So you're going in this clockwise rotation, or if you're at that 12 o'clock position, you're going towards the right. But remember, so this would be R, right? But remember, because the hydrogen is coming out at a wedge, you have to reverse the absolute configuration, and therefore it'll be the S form, and this would be an L amino acid, and therefore it is biologically active. Now, very important over here, you only reverse the absolute configuration if the lowest priority group is coming out at a wedge. So if any of these other groups, if the side chain, the amino group, the carboxylic acid group are coming out at a wedge, you're not going to reverse the absolute configuration, only if that lowest priority group is. All right, my fellow pre-meds, well, that concludes our slide deck for today. This is a high yield topic on the MCAT, and it is a bit tricky, so if you got tripped up anywhere along the video, be sure to watch it again, and you can reach out to me for any help. You know where to reach me. If you've found this video helpful and like the way I teach, I'd recommend watching the rest of the playlist. I spent a lot of time making sure that the videos build on one another, so it makes sense to watch them in order. Also, don't gatekeep these videos. If you have a friend who's currently studying for the MCAT, be sure to share the playlist with them. It really helps the channel grow, and I would really appreciate it. Also, did you know that every single video has customized Anki cards associated with it that cover the concepts that we discuss in a video? So if you want a way to be able to actively review the material and retain it for the long run, I've got you covered. If you're interested in accessing the Anki cards or even the slide decks within the videos, then check out our Patreon or reach out to me directly for alternative ways to access the Anki cards and the slide decks. Finally, these videos, at least as of now, are sponsored by you. So if you're interested in supporting me to be able to continue to make these high quality MCAT playlists, you can support me either via Patreon or by buying me a coffee. Links in the description down below, as well as the links for everything else, including the link to our growing pre-med companion Discord community. Thanks for watching, and I'll see you in the next video.